Day 130, examples of Coulomb's law, the electrical force between charged particles. We're going to compare that here in this problem number 2 to the gravitational force of attraction between the electron and proton in the hydrogen atom. If this red dot represents a proton, then the orbiting electron by this circle, and let's say this is the electron right here, this little blue dot, they're attracted for two reasons, gravity and electrical attraction. So I'm going to show that they're attracting each other. They both pull on each other equally in both those cases. I will do two separate calculations. First for the force of gravity, F sub g, which is g m1 m2 over r squared. So F sub g, usually we use little g, F sub g is 6.67 times 10 to the negative 11th times the product of the masses. Because of space here, I'll just put m sub e, mass of electron, times mass of p, proton, given off to the left. I'll be plugging those numbers in. These are the numbers over here that'll be plugged in there on your calculator, divided by the radius between them squared, which is the 5.29 times 10 to the negative 11th meters. That quantity has to be squared. It's one thing that's forgotten a lot, is squaring that denominator. Anyway, if you plug all those numbers in there, the gravitational force of attraction comes out to be 3.6 times 10 to the negative 47th newtons. That's a really small force of attraction because they're small masses. But what does the force of the electrical force look like? F sub E is K times Q1 times Q2 divided by R squared. So the electrical force here is 9 times 10 to the 9th, Coulomb's constant, times charge number 1. Well, they both have the same charge. The electron and proton are both 1.60 times 10 to the negative 19th. Okay, I could write that twice, or a faster way to write that would be squared. You don't need to worry about the negative. The negative only tells you in the electron that they're going to attract each other, so we don't plug in the negative to the equation. It's already taken care of, like with the arrows in the diagram. Divided by the same radius, the 5.29 times 10 to the negative 11th, quantity squared. So you go to your calculator, plug that in. The electrical force of attraction, because one's a negative, one's a positive, opposites attract, is 8.3 times 10 to the negative 8th. 8.3 times 10 to the negative 8th newtons. That's also a small force, but it's nowhere near as small as the gravitational force. So if we look at these two boxes here, just for a moment, we can tell that the electrical force is much, much, much greater than the gravitational force. It's the one that dominates. It's the one that actually keeps the electron in orbit. Gravity is insignificant here. But the problem does say to compare up at the top here. And one way to compare is two numbers when they're vastly different like this is just to simply see how much bigger the bigger number is. So in this case, I'm just going to take the ratio, take the big number over the small number. In other words, I want to take F sub E, the electrical force, over F sub G. How much bigger is the big force? So that will be 8.3 times 10 to the negative 8th. Once again, this is a good way to compare two numbers that are vastly different. If they're close, then you do it by percent differences. But here they're not anywhere near in the same ballpark. Divided by 3.6 times 10 to the negative 47th. And if you round off here, it comes out to be like roughly 2 times 10 to the 39th. Or if you just even get rid of the 2, it's basically roughly equal to 10 to the 39th. A ratio of 10 to the 39th. That's a 39 there. Or in other words, the electrical force, F sub E, equals roughly 10 to the 39th times the gravitational force. That's a good way to compare two numbers that are vastly different. Sorry about scrunching this in this little space here. Example number 3. A rubber balloon is rubbed with some fur, and it picks up some electrons from the fur. The fur was neutral, so it had equal number of electrons and protons. Basically, part A is asking what charge must the fur have? Well, it lost electrons, and it was neutral, so now it's positive. It's positive by the amount that the balloon is negative because of conservation of charge. In other words, the fur will be plus 0.15 microcoulombs. That's the charge on the fur. That little mu there is micro. That's 10 to the negative sixth prefix in metric. But part B now is how many electrons does it take to make that much charge? Essentially, it's kind of like asking the question, if I have $532.65 worth of nickels, a pile of nickels, how many nickels does it take to make that pile? Well, essentially, you just take the big number, the $535, whatever number I mentioned there, and divide by the small number, the 0.05 cents for a nickel. Here we're going to take the big number, the 0.15 microcoulombs is the big number. That's times 10 to the negative sixth coulombs, divided by, like, the worth of a nickel, or the worth of an electron, which is 1.60. It's the fundamental charge, times 10 to the negative 19th, which is very, very, very small. How many of these small guys does it take to make that big guy? You simply divide. And when you do that, it comes out to be 9.4 times 10 to the 11th. 9.4 times 10 to the 11th electrons. Now, that seems like a lot of electrons, and it is, but there's like on the order of like 10 to the 20th or 10 to the 21st or 22nd electrons on that fur or in that balloon to begin with, so this is a very small percentage of electrons available, but it does pick up electrons to become charged negatively, and the fur then becomes positively charged because it lost some electrons after being neutral. Example number 4. All right, here we have 3 collinear charges. We have a plus 5 microcoulomb charge in line with a negative 4 microcoulomb charge and a negative 3 microcoulomb charge. Once again, they're all in a straight line to make this problem easy. It will be a vector problem because, once again, forces are vectors. That'll come into play big time here in this problem. It says calculate the net force on each of the following 3 charges. So there we go. I'm also told, I'm giving you, that this distance here between the 5 and the 4 is 20 centimeters. And the distance between the 2 negative charges is 10 centimeters. All right, this is kind of like 3 problems in one in a sense. What I need to do is take these 2 at a time because Coulomb's law allows me to calculate the force between 2 charges with the equation using F equals K, it's a K, Q1, Q2 over R squared. So for example, if I look at the 5 and the 4, the 5 and the 4 microcoulomb charges are going to attract each other. I'll show that in a diagram with arrows. They're going to attract each other equally in opposite directions. I'm going to call that F sub 1 and F sub 2. F sub 1, F sub 2. But F sub 1 is going to equal F sub 2. I'll do this computation over here on the right. F sub 1 equals F sub 2 equals K times the product of the 2 charges. K is 9 times 10 to the 9th times the 2 charges. I have 5 microcoulombs and 4 microcoulombs. So it's going to be 5 micro. I've got to remember to plug in 10 to the negative 6th on my calculator there. Times 4. Once again, I can ignore the negative. I've already taken care of that with the arrows in the diagram. The negatives are only a directional thing showing me that the 2 charges here attract each other. All right, so, and the distance between them is 20 centimeters, which is 0.20 meters squared. All right, so F1 equals F2. You plug it all into your calculator, making sure you put in 10 to the negative 6th for the micro, and you end up with, I believe, 4.5 newtons. They're attracting each other with a force of 4.5 newtons. That's not the answer to the problem, but it's going to be an important piece to get to the answer, so I'm going to box that in right now. And now I'm going to look at the 4 and the 3. The 4 and the 3 are both negative, so they are going to repel each other. The way I'm going to show that in a diagram is with repelling arrows, vector arrows. Those two charges repel. I will call that F sub 3 and F sub 4. F sub 3 and F sub 4, and they're equal. F sub 3 equals F sub 4 equals 9 times 10 to the 9th times 4 microcoulombs times 3 microcoulombs divided by 0.10 squared. So F3 equals F4 comes out to be 10.8 newtons. Much stronger force because they're closer together. Just based on distance alone, it should be 4 times stronger because half the distance should give you a force that's 4 times stronger. However, the one charge is weaker, the 3 is weaker than the 5, so the net result is not a 4 times stronger force. 10.8. All right, we have one combination left, the 5 and the 3. The 5 and the 3 attract each other. I'll use red arrows for that. So my diagram's getting a little messy here, but the 5 and the 3 attract each other, so I'm ignoring the 4 right now. So the way I'm going to show that is with vector arrows once again. I'm going to show that the 5 will be attracted to the right and the 3 attracted to the left. I can call those F 5 and 6 for lack of better terminology. I should say F5 there and F6, showing those two forces attracting each other. I'm a little out of space, but I'm going to impinge upon the next problem here. F5 equals F6 equals 9 times 10 to the 9th times 5 microcoulombs times 3 microcoulombs divided by, and I'll be careful with the distance here, it's 0.30 meters, 30 centimeters, 0.30 squared, don't forget to square that. F sub 5 equals F sub 6 equals 1.5 newtons. That's the weakest of the 3 pairs of forces because of the greater distance. When the distance goes up, the force goes down very quickly because the distance is squared and you're dividing by that. It's an inverse square relationship. All right, now we're ready to get to the answer. If we look at these one at a time, I want to find the net force on the 5 microcoulomb charge. So let me go over here to the left. I'll use black. So F net for the plus 5. I'll put F net 5. What it is just going to be the sum of F1 plus F2. I'm looking at the diagram and I see F1 and F5 are the two forces applied to that that charged particle. So I'm simply going to add F1 and F5. If I look over to the right, F1 is 4.5 and F5 is 1.5. I add 4.5 plus 1.5. I can write that out for you if you want. 4.5 plus 1.5 comes out to be 6.0 newtons. And you must say to the right, 6.0 newtons to the right. That's the net force on the 5 microcoulomb charge. How about, I'll use red, for the middle, the 4 microcoulomb charge, F net for the 4 microcoulomb charge, negative 4, equals, if you look at the diagram, color-coded now, F sub 2 is black, F sub 3 is blue. They're both pointing to the left. They're going to add to the left. So I look at F2 and F3. I'm going to add 4.5 plus 10.8. 4.5 plus 10.8, which gives me 15.3. 15.3 newtons to the left. And finally, I'll do blue, the F net for the 3 microcoulomb charge. All right, now in this case, it has opposing forces. F6 is to the left, and F4 is to the right. So you want to take the bigger force minus the smaller force. They're not in the same direction, so we're not going to add like we did for the other two. I will take the bigger one, 10.8, subtract the 1.5. So the net force on this charge will be, what, 9.3? 9.3 newtons. And what is the direction? Well, it's in the direction of the larger force. The F4 was the bigger force, so that will be to the right. So those are your three net forces on those three charges.